Hey, I'm Sean, and today I'll be discussing how rotational motion plays a key role in drifting. But what exactly is rotational motion? Rotational motion is the circular movement of an object. We can analyze this circular movement using these four equations. These are our rotational UAM equations, and I know they may seem complicated, but once you understand them, they actually are pretty simple. But before that, we have to understand what all these fancy symbols and variables mean. First, the circle with a line through it, or theta, is the angular position or how much the object has rotated from its original position. This is primarily described in radians, which you'll probably remember from your math class, along with the unit circle. To convert to radians, you simply take the degrees, multiply it by pi, divide by 180, and congratulations, you just successfully converted to radians. The next symbol I want to talk about is this curly looking W, or the Greek letter lowercase omega, which is the angular velocity of the object. And since velocity is a vector, it tells you that the object's magnitude, or how fast it's rotating, and the direction in which that object is rotating, in which counterclockwise is typically positive, and clockwise is typically negative, just like the order of the quadrants on a coordinate plane. It is determined by dividing the change in angular position by the change in time, using a lowercase t. Like angular position, angular velocity is usually described in radians per second. The last fancy variable in these rotational UAM equations is this fancy looking a, or Greek letter alpha. It stands for the angular acceleration, which simply put is how much the angular speed is changing over a certain period of time. For example, when you step on the gas, the wheels are going to turn faster, and thus their angular acceleration is increasing. The opposite is true when you hit the brakes. When you hit the brakes, the wheels rotate slower, and thus the acceleration is working in the negative direction. Alright, so now that we know what all these variables actually mean, let's take another look at those equations. As you can see, when we compare these rotational kinematic equations to our linear kinematic equations, you will see that they are essentially the exact same equations. In fact, we can derive these equations using the exact same techniques, whether it be using the area under the line of an angular velocity versus time graph to determine the change in angular position, or the area under the line of an angular acceleration versus time graph to determine the change in angular velocity, or using the previously mentioned equations to derive another equation to find the change in angular velocity, or simply finding the average angular velocity and multiplying it by the time to find the change in angular position. We can convert from our linear position, velocity, and acceleration values to our rotation values by multiplying the rotational motion variables by the radius of the wheel. However, this is only the case when the wheels are not slipping. A car drifting is a prime example. When a car is drifting, its front wheels keep track of its rear, and its back wheels are slipping, as clearly shown by the smoke coming from the rear tires. Meaning that without knowing how much the tire is slipping, we can't determine the linear values of the rear wheels from our rotational values. The reason for this slipping is because the frictional forces exceed the maximum amount of static friction, and thus becomes kinetic friction. Now, depending on how much you may or may not already know about physics, you may be wondering how the bottom of the tire has static friction if the tire is still rotating and moving. And to understand this, you first need to know that when you are driving and the tires are not slipping, the wheels are moving with both a rotational velocity and a linear velocity. When an object is moving linearly, it is not spinning and is simply moving from point A to point B. This means that the object has just one total linear velocity. However, rotational velocity is a little bit more complicated. When a wheel is spinning or rotating, it has one rotational velocity. However, it has several tangential velocities. Tangential velocities are velocities that are tangent to the circle or wheel. For example, when a wheel is spinning clockwise, it has tangential velocities that may look something like this. It's important to remember that because velocity is a vector, the different tangential velocities are not equal despite having equal magnitudes. Another thing that's worth mentioning is that because the tangential velocities are changing directions as the wheel is spinning, there must be a net centripetal force or acceleration that is changing the direction of the tangential velocities. Alright, now that we've discussed the tangential velocities, let's discuss angular and linear velocity. If you remember, the key difference between the two is that angular velocity is a change in angular displacement over time, while linear velocity is a change in linear displacement over time. You're probably thinking to yourself, okay, Sean, but why is this important? And that's a great question, and here's why it's important. Let's place 2 points on this tire. We will call this point A and this point B. As you can clearly see, point A has a much larger circumference than point B, yet when the wheel completes one revolution, the 2 points finish at the same time. This is because the 2 points have the same angular velocity and are completing 2 pi radians in the same amount of time. However, point A has a greater linear velocity since it's traveling at a greater linear distance than point B in the same amount of time. In fact, you can clearly see this when I complete the math of the linear velocity of the 2 points, if they complete a revolution in 5 seconds. This makes sense because if you remember our conversions from our angular values to our linear values, we just simply multiply the rotational values by the radius. And since angular velocity is the same for both points and the radius for point A is greater than point B, the linear velocity must be greater. In fact, if you wanted to take this a step further, you could say that the person sitting in the back seat of a car that is drifting is moving with a greater linear speed than a person sitting in the driver's seat. This is again because the person in the back seat is further from the axis of rotation than the person sitting in the front seat. But anyway, back to the wheel. When you're driving in general, your wheels are moving with both a rotational and linear velocity. So to figure out how fast each part of the wheel is moving, let's just add these two velocities together for the total velocity of the top, bottom, and center of the wheel. As you can see, the rotational and linear velocities are moving at the same speed and thus have equal magnitudes. First, if we look at the top of the wheel, we can see that the linear velocity and the rotational velocity have both the same magnitude and direction. So when we add the two together, we get a velocity that is the sum of both. When we look at the velocities at the center of the wheel, we see that since there is no rotational velocity, is only equal to the linear velocity, which if you look at the center of the wheel when it's rolling, the vertical position of it is not changing. When we look at the sum of the velocities at the bottom of the wheel, we see something interesting. The rotational velocity and the linear velocity cancel each other out, meaning that the bottom part of the wheel is not moving for that brief moment it is in contact with the ground. This is the same thing as when a person is walking. When a person is walking, their back foot stays stationary while they push off the ground to take their next step. However, the rest of the person is continuing to move forward. And since the bottom of the wheel has a velocity of 0, for that brief moment it is in contact with the ground, static friction is present. Now that we've discussed how rotational motion occurs, let's talk about why rotational motion occurs, which is a great segue into my favorite part of rotational motion, torque. Torque is the ability for a force to rotate an object. It is indicated by the Greek letter tau. Typically measured in Newton meters or foot-pounds for us Americans, the torque is equal to the radius times the force times the sine of theta, or the angle in which the force is applied. It can also be written as the moment arm, also referred to as the lever arm, times the force. Now you're probably thinking to yourself, Sean, what in the world is a lever arm? And don't worry about it. I got you. The lever arm, or moment arm, is the line that is extended from the axis of rotation and is perpendicular to the line of action, which is simply the extension of the force on a force diagram. This creates a perfect right triangle, in which the radius is the hypotenuse, the force is the adjacent leg, and the moment arm is the opposite leg. This can better be seen once we rotate our triangle. We can now substitute our values into our sine trig function and multiply both sides by the radius. Once we do that, you can clearly see that the moment arm is equal to our radius times the sine of theta. We then multiply our force by our newly found moment arm. This is why the equation is set up the way it is. It wasn't for some random reason that people happen to stumble upon. There is a logical explanation for it. We can now take this equation and analyze how changing the different values of the equation changes the overall torque. When you increase the radius, you're making one of the variables bigger, and thus the torque will obviously increase. The opposite is also true. When the radius decreases, the torque also decreases. This is why it's easier to break a pencil with your hands farther apart rather than right next to each other. It is also the reason why mechanics use large socket wrenches like these to loosen bolts that are on tight. Let's say you have two wrenches, one that is 1 meter in length and another one that is 2 meters in length. If you apply 1 newton of force on each wrench, the smaller one will generate only 1 newton meter of torque, while the larger one to the radius, the total amount of torque will directly correlate with whether or not the total amount of force that is being applied is increased or decreased. However, there is one key component of the equation that we still must analyze. A force can be applied at a variety of different angles. To understand this better, let's look at a sine curve. On this graph, we can assume that the radius and the amount of force that is being applied is constant. We can also say that the vertical axis represents torque and the horizontal axis represents the different angles that the force can be applied. You can clearly see on the sine curve that a force applied at a 270-degree angle will cause the greatest amount of torque in the positive direction, and a force applied at a 270-degree angle will cause the most amount of torque in the negative direction. We can also see that a force that is applied at a 180-degree angle will never generate any torque. Finally, we can understand one more thing. Our force and radius in our equation are used to scale this pattern either up or down. This means that if you increase the radius or the force, the graph will have a higher maximum and a lower minimum, and vice versa. Thus, a 90-degree angle will always generate the most torque possible, and a 180-degree angle will never generate any torque. This is how the values and variables that are used in this equation are crucial to the amount of torque that is created. But where exactly can torque be found in drifting, or just a car in general? When people are comparing their cars, most likely you'll hear them talk about how much torque their cars produce. But what exactly does this mean? To answer this question, we have to take a closer look at what's going on under the hood. When you're driving, a small explosion occurs in the combustion chamber of your engine. This explosion applies a force on the piston and the crank pin. This causes the crank pin to rotate with the center axis, or the crankshaft, to eventually get it to rotate. This rotation of the crankshaft is the reason why your wheels rotate. The more torque that is created, the more powerful your car will be. More torque can be created using a variety of different methods, such as having more cylinders in the engine or by using a more combustible fuel. How quickly this torque can be created is called horsepower, which is another important statistic used when comparing cars. 1 horsepower is equal to approximately 44,711.5082 newton-meters of torque per minute. But why 44,711.5082 newton-meters? Well, it all started with this famous Scottish inventor named James Watt, who determined that a horse could generate 33,000 foot-pounds of torque in a 1-minute period, or in other words, lift 330 pounds 100 feet in 1 minute. We can then convert our mass and displacement into kilograms and meters. Then we can use our gravitational force equation to multiply our mass by Earth's gravitational acceleration of 9.8 meters per second. We then get how much newtons of force the 149.685 kilograms is generating. If we then multiply our 1,466.913 newtons of force by a displacement of 30.48 meters, we see that the horse is generating 44,711.5082 newton meters of torque. Today, we use a machine called a dynamometer, or also called a dyno. The dyno is connected to the crankshaft to measure the amount of torque the engine creates when the car is running at full throttle. The dyno also applies a load to the engine to regulate its RPMs, because otherwise the engine would run so fast it would just explode, and it might do something like this. We can use the torque and RPMs calculated by the dyno to determine the car's horsepower using this equation. But why are we dividing by exactly 7,116.057543? Remember how the horse was able to move 149.3685 kilograms, 30.48 meters to generate 44,711.5082 newton meters of torque? Well, if that's true, then the horse theoretically should be able to lift 0.10204082 kilograms, or 1 newton of force, 44,711.5082 meters, since in both scenarios the horse is generating 44,711.5082 newton meters of torque. Now let's add something to the situation. Let's say that as the horse pulls the rope turns a wheel that has a negligible friction. And for easier math, let's assign the radius of the wheel as 1 meter. To figure out how many times the wheel is going to rotate, or its RPMs, we have to divide the length of the rope, 44,711.5082 meters, by the circumference of the wheel, or 2 pi. And if you punch that into your calculator, you will see that it miraculously equals 7,116.057543. Now you're probably like, that's great, Sean, but that really doesn't explain why we use this in our equation. Alright, simply put, when we divide the rotations per minute generated by the engine by the rotations per minute in 1 horsepower, we are determining what percentage of the RPMs in 1 horsepower we are producing. This makes sense because the greater the frequency in that 1 minute period where the pistons are going up and down, the more torque the engine is going to produce. Thus, what we are truly doing in this equation is multiplying the torque by the frequency of the crankshaft's rotation in a 1 minute period relative to the frequency of the crankshaft's rotation, or the wheel in the example with the horse, that is in 1 horsepower. This is how we can calculate the horsepower of a car using its torque. The next thing we do is measure the torque and calculate the horsepower at different RPMs by either increasing or decreasing the load that is applied to the engine. When we do this, we create a graph that looks something like this. The first thing I would like to mention is that dynos typically measure torque in foot-pounds. Thus, rather than using this equation, we will use this similar equation. The only two differences between the two equations is the fact that we measured the torque in foot-pounds and that we use 5,252 as the denominator rather than 7,116.05754 to account for the imperial conversion. The equation is still used and derived the same way, it's just that we use a different unit of measurement. The next thing that I would like to note is that horsepower and torque are equal at around 5,252 RPMs. This makes sense because the frequency of the rotations of the crankshaft in the car is equal to the frequency of the rotations of the crankshaft in 1 horsepower. Thus, when you divide the two, you get the horsepower is equal to the torque times 1, which is simply just the torque. The last thing that is important to note is that the max torque and the max horsepower are at different RPM ranges. The max amount of torque is found at a lower RPM range than the max amount of horsepower. For this reason, people downshift to accelerate around people when they are racing in order to get closer to that RPM range where horsepower is at its greatest. Conversely, when people are starting from rest and trying to get as much power to their tires as possible, they rev their engines to try and get closer to that RPM range where torque is the greatest. This goes beyond just racing. It plays a crucial role in why diesel trucks and semis are used to carry heavy loads rather than your mom's old Honda Civic. It is also why you rarely see some country boy with a stock diesel truck roll up to the drag strip. A diesel engine typically has more distance between the crankshaft and the crankpin, or throw. This means that it's going to create more torque since the radius is greater than a normal gas engine. However, it's going to take longer for the crankshaft to make one full revolution, which is going to decrease the horsepower. For this reason, a diesel truck is a lot like a bodybuilder. They can lift a heavy load, but they're not so good for being as agile as someone who is smaller. Now that we've talked about torque, let's talk about momentum, more specifically angular momentum. Angular momentum works almost the exact same way as linear momentum, in which angular momentum is a principle of an object that states that an object that is rotating will continue to rotate, and an object that is not rotating will continue to not rotate unless acted upon by a net external torque. This is Newton's first law of motion, also referred to as Newton's law of inertia. We can use our linear momentum equations and make a few changes to get our angular momentum equations. Now you may notice one key difference between the linear and angular momentum equations, and that is that we changed the mass of the object when we calculated the linear momentum to a capital I. This capital I stands for the rotational inertia of the object. The rotational inertia of an object is how easily or how difficult it is for that object to maintain its rotational velocity. This is why tires are designed to be circular shaped rather than square, because a wheel has more rotational inertia than a cube, and the wheel is going to want to continue to rotate more than the cube will. This is also why people play craps with cube die rather than sphere die, because otherwise the die would want to and would continue to roll until all the kinetic energy is transferred out of the die. That and the fact that you couldn't figure out which side the die landed on, but I mean, you get what I'm saying. Now I get it, you're probably like, Sean, enough with all this other random information. What does any of this have to do with drifting? And let me tell you, it has everything to do with drifting. Think about it. When you get in your car, you don't just automatically begin to drift the second you turn your car on. No, you have to start driving first, and when you begin doing this, you're building up your linear momentum, as Tommy discussed in his portion of the video. Now as you're driving, the tires still have traction, and there is still static friction between the tires and the asphalt. But when you want to start drifting, it's more than just turning the wheel in the direction you want to start drifting. It's a perfect mixture of gradually hitting the brake and popping the e-brake. And if you do the thing, and you do it right, and you don't mess it up, your back tires will lose traction and you'll begin drifting. Why does this work? Well, it's because the rear wheels have exceeded the maximum level of static friction and now have kinetic friction with the asphalt. This means that the rear of the car is sliding and will want to continue in that direction of the original linear momentum. However, there is one important thing that doesn't allow the car to keep going in that direction, and that's the front of the car. When you are drifting, your front wheels should be turned in the in direction of the drift. And since the front wheels still have traction, they will provide a centripetal torque in the in direction of the drift. Let's take a closer look at that torque. You remember our torque equation? Torque equals radius times the force times the sine of the angle of the force. Well, that's very important here because it's how the driver is able to control the drift. When the driver wants to drift more, they hit the gas so that the tires are generating more static friction more often. This causes for a greater torque, and thus, using our rotational motion version of our centripetal acceleration equation, we can determine that there will be a greater centripetal acceleration. The driver can also achieve the same thing by turning more into the drift, because the closer the driver can get to turning his wheels 90 degrees, the more torque the wheels are going to provide. And just like how increasing the force increases the torque, and the more centripetal acceleration that will be caused. Without this centripetal acceleration, you might see something like this, which, believe me, is not good for anybody in that situation. If you want to drift less and slide more, you can hit the brakes or countersteer by turning the wheels away from the drift. When they are done drifting, they turn the wheels in the opposite direction. What this does is it decreases the torque, and so the car will continue to follow its inertia or tangential velocity. This also means that you're decreasing the slip angle. When you do this, the rear tires begin to lose some of that frictional force until it becomes static friction and regains traction with the ground. Now when you're drifting, the total momentum is conserved, as stated by the law of conservation of momentum. This means that at any point in the drift, the car must have the same momentum. Thus, when the car is entering the drift, it is losing its linear momentum and gaining more rotational momentum. The opposite is also true. When the car is exiting the drift, it is losing its rotational momentum and gaining its linear momentum. The last thing I want to talk about is the fact that movies make drifting seem as if it was the fastest way to take a corner, and this couldn't be more wrong. In fact, even some of the fastest cars in the world, such as Formula 1 cars, try to avoid drifting at all costs by increasing their wheels' max static friction. This actually makes sense because when a car is drifting, its rear wheels have the whole kinetic friction thing going on, which is approximately 85% or less than the frictional forces of a tire with static friction. And the more force the object has, the greater its acceleration. So if we look at our rotational UAM equations, more specifically this one, and we assume that the car is traveling around the same track with the same initial velocity, we can clearly see that increasing the acceleration would decrease the total time. This is why you never see NASCARs or Formula 1 cars drifting in the middle of a race. The point is, rotational motion plays a crucial role in drifting and has multiple aspects to it. I hope you enjoyed this video and I hope you have a great day. Thank you so much, and I'll see you next time.